So we've talked about the fundamental counting principle, and now we're going to take it a little bit further and talk about the sample space. In probability, the sample space of an experiment is the set of all possible outcomes. And we use a capital S when we talk about the sample space. So, for example, a simple problem, let's say we are going out to a party, we want to know what to wear. We can wear a top and a bottom. And let's say for the top, I have three options. I have a red shirt, a green shirt, and a blue shirt. And for the bottom, I can either wear pants or shorts. Now, all my options, which is what you did before, is just to simply list it. I could go red with pants, green with pants, blue with pants, or I could go red with shorts, green with shorts, or blue with shorts. So how many options were there? There were 6. This is the number we're going to be interested in. We are now interested in the size of the sample space. We don't really care how we got them by listing it like this. We are more interested now in this number right here, the size of the sample space. How many total options are there? What you should notice from this problem, and maybe you recognized this before, the number of tops we had 3 options. The number of bottoms, we had 2 options. 3 times 2 gives me my answer down here, 6. And we're going to take that a little bit further to talk about the size of these sample spaces. The easiest example we can do is flipping coins. The sample space for one coin, capital S, we'll use set notation, is heads or tails. Those are the only options I could get for one coin. So then the size of my sample space would be 2, because there are only 2 possibilities. Now, if I'm going to flip 2 coins, I have the sample size, or the sample space for my first coin, which can either be heads or tails, and I have the sample size, or sample space, for my second, which also can only be heads or tails. So I have 2 options for the first coin, and I have 2 options for the second coin. Just like we did on the last problem, if we multiply the sizes together, 2 times 2, I will get my overall size, which is a 4. The last one, same idea. For the first coin, I have 2 choices. Second coin, 2 choices. Third coin, 2 choices. Third coin, 2 choices. So to find the total overall size for flipping 3 coins, it's just 2 times 2 times 2. There are 8 possibilities. Now, could we write them all out? For example, could we write heads, 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 tails, and so on? Of course. But I don't want to do it 8 times. I want to find that shortcut. It gets even trickier when we start talking about dice. Now, dice are just a little bit harder because instead of 2 options, heads or tails, we now have 6 options. Notice that we're assuming that we're using 6-sided dice. Not all dice have 6 sides, and it will specify that in a problem if it doesn't. So the sample space for one dice, or one die, singular, is 1, 2, 3, 4, 5, or 6. So that means that the size of that sample space must be 6 choices, or 6 possibilities. Now, if we do it for 2 dice, we have dice 1, there's 6 choices. Dice 2, also 6 choices. So the sample space total, just like we did before, is going to be my 6 choices times my 6 choices. That means that there are 36 different possibilities if we're rolling 2 dice. Now, could I write them again? Could I write out, I could get a 1 and a 1, I could get a 1 and a 2, I could get a 1 and a 3, I could get a 1 and a 4, and so on? Of course. But you're going to have to write all 36 of those possibilities. It's going to be much faster if you simply multiply them together. Marbles. A jar contains 1 red, 3 green, 2 blue, and 4 yellow marbles. Well, let's add those up. 1 and 3, 2, 4, That's going to mean that there's 10 marbles total in the jar. If a single marble is chosen, what is the size of the sample space? In other words, how many possibilities do I have? Well, there's 10 marbles to choose from, so my sample space, or the size of my sample space, is I have 10 possibilities. I don't know what I'm going to get, but it has to be one of those 10 marbles in the jar. If 2 marbles are chosen, what is the size of the sample space? Now here it gets a little tricky. There are 2 options. We can either say it is with, you can either say it is with replacement or we can say it is without replacement. And you have to be very careful. Without replacement. If it's not given to you, you have to assume that you're not replacing it. The default is without replacement. However, in some problems it will say it's with replacement. So we're going to do both and talk about the difference. With replacement simply means you pull your marble out. So let's say here's my blue marble. Here's my jar. I'm going to pull my blue marble out. Then I'm going to put it back in. And then I'm going to draw my next one. So that means that we draw it, we look at it, we put it back in, we replace it, and then we draw our second one. So if we talk about with replacement, my first time I pick a marble, there's still 10 marbles. So my first time there's 10 choices. I take it out, I look at it, I put it back in. Then, when I take my second marble out, there are still 10 marbles, because it's possible that I could still get this blue marble again, because I put it back inside. So with replacement, it's 10 times 10. That means that there are 100 possibilities. Okay? So there are 100 different possibilities of which 2 marbles I could take out. However, without replacement, it changes a little bit. So let's go back to my blue marble. Let's say I grab my blue marble, I take it out. This time, I'm not going to put it back in. So for my first marble, once again, I had 10 options, right? Because there was a full jar of 10 marbles. But then, when I take out a second marble, the blue one is now no longer inside. So instead of 10 marbles to choose from, I only have 9 marbles. So if it's without replacement, I now only have 90 possibilities. So you have to watch out as to whether it's with or without replacement, because that will make a big effect on the number of possibilities. The last problem is the most complicated. How many license plates are possible here? Well, this is Missouri's plates, and they follow the same standard for all their plates. They have numbers first, 3 of them, and then letters. So what we need to do here is consider each one at a time. So if we look at our first number, it could be one of any one of the digits. So it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That means that there are 10 possibilities for this first digit. So if we're looking at our first digit, it's going to be 10, because it could be one of 10 digits. The next one, also a digit, well, there's 10 of those, because we can repeat. It doesn't matter if we repeat or not. And the last one, also 10. For the letters, we know that there are 26 letters in our alphabet. So instead of 10 now, when we're looking at the letters, we have 26 possibilities. So for each one of these last 3 letters, there are 26. And just like we've been doing, this is just a more complicated example, we need to take the possibility of each one of these and multiply them all together. And I've already done that. You get a very large answer, 17576,000. So there are 17.5 million, 17.5 million, roughly, possibilities for license plates. And that makes sense, because when you think about all the cars on the road in any given state, you need to have a lot of possibilities so that you don't have repeats. Hopefully this has been a good introduction. Now you're going to try some of these on your own and then with a partner.